algorithm up here. I'm going to write it out for the 1D version. So what we have here is a recursive algorithm. So the picture you want to keep in your head is this picture that I put up there, and this is the divide and conquer algorithm. You're going to see this over and over, this paradigm, over and over in 606. We're going to look at the n over 2 position, and I'm going to look to the left, and you're going to look to the right. And you're going to do that in sequence. So if a n over 2 is less than a n over 2 minus 1, then only look at the left half, 1 through n over 2 minus 1, to look for peak, or peak. Right, so that's, you have one, you have it on the right side or the left hand side, doesn't really matter. I chose to do the left hand side first, the left half. So what I've done is, through that one step, if in fact you have the condition a n over 2 is less than a n over 2 minus 1, then you move to your left and you work on one half of the problem. But if that's not the case, then if n over 2 is less than a over n by 2 plus 1, then only look at n over 2 plus 1 through n for a peak. So I don't bother writing out all the words. They're exactly the same as the left hand side, you just look to the right hand side. Otherwise, if both of these conditions don't fire, you're actually done. Okay, that's actually the best case in terms of finishing early, at least in this recursive step. Because now the n over 2 position is a peak. Because what you found is that the n over 2 position is greater than or equal to both of its adjacent positions, and that's exactly the definition of a peak. So you're done. Okay, so all of this is good. You want to write an argument that doesn't I'm not going to bother with that. I just wave my hands a bit, and you all nodded, so we're done with that. But the point being, you will see in your problem set a precise argument for a more complicated algorithm, the two versions of this, and that should be a template for you to go write a proof or an argument, a formal argument that a particular algorithm is correct, that it does what it claims to do. And in this case, it's 2 3 lines of careful reasoning that essentially say, given the definition of the peak, that this is going to find a peak in the array that you're given. All right. So we all believe that this algorithm is correct. Let's talk now about the complexity of this algorithm. Because the whole point of this algorithm was because we like the theta n complexity corresponding to the straightforward algorithm. So we'd like to do that. So what I'd like to do is ask one of you to give me a recurrence relation of the kind, t of n equals blah, 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 that would correspond to this recursive algorithm, this divide and conquer algorithm. And then using that, I'd like to get to the actual complexity in terms of what the theta of complexity corresponds to. Yeah, I got it.
So, even to be somehow not fine.
Yep.
Plus,
Great, exactly right. That's exactly right. So if you look at this algorithm and you say, from a computation standpoint, can I write an equation corresponding to the execution of this algorithm? And you say t of n is the work that this algorithm does on as input of size n. Okay? Then I write this equation. And this theta 1 corresponds to the two comparisons that you do, looking at potentially the two comparisons that you do, looking at the left hand side and the right hand side. So that's two of the constants, so that's how you put theta 1. Alright, so you make equation 2. That's our best. Whoa, that was bad. Beer's left. Alright, beer's left. So if you take this and you start expanding it, eventually you're going to get to the base case, which is t of 1 is theta 1. Right? Because you have a one element array, you just collapse the array, just going to be done as a peak. And so if you do that and you expand it all the way out, then you can write t of n equals theta 1 plus theta 1, and you're going to do this log to the base 2 of n times. And adding these all up gives you a complexity theta log 2 of n. Right? So now you compare this with that, and there's really a huge difference, there's an exponential difference. If you code out this algorithm in Python, and I did both these algorithms for the 1D version, and if you run it on n being 10 million or so, then this algorithm takes 13 seconds. Okay, the theta n algorithm takes 13 seconds, and this one takes 0.001 seconds. Okay, huge difference. So there's a big difference between theta and theta log n. It's really the difference between 2 raised to n and n. It makes sense to try and reduce the complexity as you see, especially if you're talking about large inputs. And you see that more clearly as we go to a 2D version of this problem. Alright, so you can't really do better for the 1D. The 1D is a straightforward problem. It gets a little more interesting. The problems get a little, the algorithms get a little more sophisticated when you look at a 2D version of peak find it. So let's talk about the 2D version. So as you imagine, in the 2D version, you have a matrix or a two-dimensional array, and you say this thing has n rows and n columns. And now we have to define what peak is, and it's a hill. It's the obvious definition of a peak. So if you had a in here, C, D, D, E, as you can guess, A is a 2D peak. If and only if A greater than or equal to B, A greater than or equal to B, C, and E. That's just a little hill up there. Alright, and again, I use greater than or equal to here, so that's similar to the 1D in the case that you always find the peak in any 2D matrix. Now, again, I'll give you the straightforward algorithm, and we call it the greedy ascent algorithm. And the greedy ascent algorithm essentially takes a direction, and it tries to follow that direction in order to find the peak. So, for example, if I had this particular matrix, 14, 13, 12, 15, 9, 11, then what might happen is if I started at some arbitrary midpoint, so the greedy ascent algorithm has to make choices as to where to start, just like you had different cases here. You have to make choices where to start. You might want to start in the middle, and you might want to work your way left first, or you just keep going left, or keep going right, and if you hit an edge, you go down. So it makes choices as to what the default reversal directions are. And so if you say you want to start with 12, you're going to go look for something to your left and it's greater, then you're going to follow that direction. If it's not, it's going to go another direction in this case, for example. So in this case, you go 12, 13, 14, 15, 16, 17, 19, and 20, and you find this peak. Now, I haven't given you the specific details of the greedy ascent algorithm, but I think if you look at the worst case possibilities here with respect to a given matrix, and for any given starting point, and for any given strategy, in terms of choosing left first versus right first, or down first versus up first, you will have a situation where, just like we had in the 1D case, you may end up touching a large fraction of the elements in the 2D array. Okay? So in this case, you end up touching one of the elements, and it's quite possible that you end up touching, starting from the midpoint, you end up touching half the elements, and in some cases touching all the elements. So if you do a worst case analysis of this algorithm, the particular algorithm, the particular choices in terms of the starting point and the direction of search, a gradient descent algorithm would have theta and n complexity. Right? And the case where n equals n, or n equals n, you have theta n squared complexity. Okay? I won't spend much time on this because I want to talk to you about the divide and conquer versions of this algorithm for the 2DP, but hopefully you're all with me with respect to what worst case complexity is. All right? People buy that? Yeah, question like that.
Can you use that calculate that you actually get to n to n?
So there are specific gradient descent algorithms and specific matrices where if I give you the code for the algorithm and give you a specific matrix, that I can make you touch all of these elements. That's right. So if you talk about worst case, that's really very paranoid when you talk about worst case complexity. And so I'm handling a bit here simply because I haven't given you the specifics of the algorithm yet. Right? This is really a set of algorithms because I haven't given you the code, I haven't told you where it starts and which direction it goes. But you go do that, fix it, and I will need version of price to find worst case complexity. Certainly, it's very easy to get to theta and n in terms of having some constant multiplying n times n, but you can definitely get to that constant being very close to 1. Okay? It's normal. All right. So let's talk about divide and conquer. Let's say that I did something like this where I just tried to jam the binary search algorithm into the 2D version. So what I'm going to do is, I'm going to pick the middle column, j equals m over 2, and I'm going to find a 1DP using whatever algorithm I want, and I'll probably end up using the more efficient algorithm, the binary search version that's all the way to the left of the board there. And let's say I find a binary at ij. If I pick a column, and I'm going to find a 1DP. So this is j equals m over 2, that's I. Now, I use ij, in particular row I, as a start to find a 1DP on row I. And I stand up here, I'm really happy, okay, because I say, wow, I picked the middle column, I found 1DP, that is theta n complexity, to find 1DP that we argued. And once I, theta n, oh, I'm sorry, you're right, the log n complexity, that's what this was, right here. Yeah, log n complexity, thanks, sir. And then once I do that, I can find 1DP on row I. In this case, the row I would be my, so it would be log n complexity. If n equals m, then I have a couple steps of log n, and I'm done. Right? Am I done? No. Can someone tell me why I'm not done? Precisely, yeah. That's exactly correct. So this algorithm is incorrect. Okay, it doesn't work. It's efficient but incorrect. Okay, it's you want to be correct. Being correct and inefficient is definitely better than being inefficient. Being incorrect and efficient. So this is an efficient algorithm in the sense that it will only take log n time, but it doesn't work. I'll give you a simple example here where it doesn't work. The problem is a 2DP may not exist on row I, and here's an example of that. Actually, this is exactly the example of that. Let's say that I started with this row. Since it's, I'm starting with this row, I'm starting with this one. Let's say I started with that one. I end up finding a peak, and if this were 10 up here, I choose 12 as a peak. And it's quite obvious that I return 12 as a peak. Here the 19 is bigger because 12 is a peak, given 10 and 11 up here. And then I choose this particular row, and I find peak on this row, it would be 14. That's a 1D peak on this row, but 14 is not a 2D peak. Okay, so this particular example, 14 will return 14, and 14 is not a 2D peak. All right. You can write the version after class. So not so good. Look like an efficient algorithm, but it doesn't work. All right. So how do we get to something that actually works? So the last algorithm that I'm going to show you, and you'll see 4 different algorithms in your problem set. That you have to analyze the complexity for and decide if they're efficient and if they're correct. But here's a recursive version that is better than in terms of complexity than the gradient descent algorithm, and this one works. So what I'm going to do is pick a middle column, j equals m over 2 as before. I'm going to find the global maximum on column j, and that's going to be at ij. I'm going to compare I comma j minus 1, I comma j, and I j plus 1. Which means that once I found the maximum in this row, I'm going to look to the left and the right and compare. I'm going to pick the left columns if I comma j minus 1 is greater than I comma j. And similarly for the right. And if in fact either of these two conditions don't fire, and what I have is I comma j is greater than or equal to I comma j minus 1 and I comma j plus 1, then I'm done. Just like I had for the 1D version, if I comma j is greater than or equal to I comma j minus 1 and I comma j plus 1, that implies ij is a 2D peak. Okay? The reason that's the case is because I comma j was the maximum element in that column. So you know that you compare it to all the adjacent elements looking up and looking down, that's the maximum element. Now you look at the left and the right, and in fact it's greater than or equal to the element on the left and the right, and so therefore it's a 2D peak. Okay? So in this case, when you pick the left or the right column, you pick one of them, you're going to solve the new problem with half the number of columns. Alright? And again, you have to go through an analysis or an argument to make sure that this algorithm is correct. But it's intuitively correct simply because it matches the 1D version much more closely. And you also have your condition that you bring away right here, where you have a 2D just like the 1D version. And what you've done is break this matrix up into half the size, and that's essentially why this algorithm works. Then you have a single column, find the global maximum, and you're done. Right, so that's the base case. So let me end with just writing out what the recurrence relation for the complexity of this is, and argue what the overall complexity of this algorithm is, and then I'll give you the bad news. Alright, so overall what you have is you have something like T of n equals T of n over 2 plus theta n. Why is that? Well, n is the number of rows, n is the number of columns. In one case, you will be breaking things down into half the number of columns, which is n over 2. And in order to find the global maximum, we're doing theta n work. So we find the global maximum. Right? You just understand it. This, that's the way that's what it's going to take. And so if you do that and you go run through, and you know that T of n1 is theta n, which is this last part over here. That's your base case. You get T of n is theta of n added to theta of n log of n times. Log 2 of n times, which is theta of n log 2 of n. Alright? So if you're not done with p-finding, what you'll see is that 4 algorithms coded in Python. I'm not going to go away what those algorithms are, we're going to recognize them. You will have seen versions of those algorithms already in lecture. And your job is going to be to analyze the algorithms as I said before, prove that one of them is correct, and find counterexamples to the ones that aren't correct. The course staff will stick around here to answer questions, statistical questions, or questions about lecture. And I will have gentlemen question.
The following content was provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Hey everybody, you ready to learn some algorithms? Yeah, let's do it. I'm Eric Devane, you can call me Eric. And last class we sort of jumped into things. We studied keep finding, looked at a bunch of algorithms, keep finding, and problems that I've already seen a bunch more. And in this class we're going to do some more algorithms. That will be at the end. We're going to talk about another problem, document distance, which will be a learning example for a bunch of topics that we cover in this class. But before we go there, I wanted to take a step back and talk about what actually is an algorithm. What is an algorithm allowed to do? And also do philosophical questions like what is time? What is the running time now? How do we measure it? And where do those game? For fun, I thought I would first mention where the word comes from. The word algorithm. It comes from this guy. So, Alex Kavazny, who is sort of the father of algebra. He wrote this book called The Compendious Book on Calculation by Completion and Balancing back in the day. And it was in particular about how to solve linear and quadratic equations. So the beginning of algebra. I don't think he invented those techniques, but he was sort of the textbook writer who wrote sort of how people solve them. And you can think of how to solve those equations as early algorithms. First you take a like this, you add it, or you reduce to squares, whatever. So that's where the word algebra comes from, and also where the word algorithm comes from. There are many words with these roots. So there you go, some fun history. What's an algorithm? I'll start with sort of some informal definitions, and then point of this lecture and the idea of a model computation is to formally specify what an algorithm is. I don't want to get super technical and formal here, but I want to give you some grounding. So when we write Python code, when we write pseudocode, we have some idea what things actually cost. This is a good lecture, we've never done this before in level 6, but I think it's important. So at high level, you can think of an algorithm as just a, it's a way to define computation or a computation procedure for solving some problem. So whereas computer code, I mean, it could just be running in the background all the time doing whatever. An algorithm, we think of it as having some input and generating some output, usually to solve some problem. You want to know, is this number prime? Whatever question. This microphone does not feed into the AV system, so I should talk louder. And quiet on set, please. Okay, so that's an algorithm. You take some input, you run through, you compute some output. Of course, computer code can do this too. An algorithm is basically the mathematical analog of a computer program. So if you want to reason about what computer programs do, you translate it to the world of algorithms. And vice versa, you want to solve some problem. First, you usually develop an algorithm using mathematics, using this class, and then you convert it into computer code. This class is about that transition from one to the other. You can draw a picture of sort of analogs. So an algorithm is a mathematical analog of a computer program. A computer program is built on top of programming language. It's written in a programming language. The mathematical analog of a programming language, when we write algorithms in, usually we write them in pseudocode, which is basically another fancy word for structured English. Good English, I think you want to say. Or you could use another natural language. But the idea is you need to express that algorithm in a way that people can understand and reason about formal structured part. Pseudocode can mean lots of different things. It's just sort of an abstract how you write down formal specification without necessarily being able to actually run on a computer. There's a particular pseudocode in your textbook which you probably could run on a computer, a lot of it anyway, but you don't have to use that version. It just needs to make sense to humans who do mathematics. Okay, and then ultimately this program runs on a computer. You all have computers probably in your pockets. There's an analog of a computer in the mathematical world, and that is the model of computation. And that's sort of the focus of the first part of this lecture. Model of computation says what your computer is allowed to do, what it can do in constant time, basically. That's what I want to do. Here. So, model of computation specifies basically what operations you can do in an algorithm and how much they cost. This is the latest time. So for each operation, we're going to specify how much time it costs. Then an algorithm does a bunch of operations. They're combined together with control flow, for loops, if statements, stuff like that. We're not going to worry about too much, but obviously we'll use them a lot. And what we count is how much each of the operations cost. You add them up, that is the total cost of your algorithm. So particularly we care mostly in this class about running time. Each operation has a time cost. You add those up. That's running time of the algorithm. Okay. So I'm going to cover two models of computation, which you can just think of as different ways of thinking. You've probably seen them in some sense as styles of programming. Object-oriented style of programming, more assembly style of programming. There's lots of different styles of programming languages. They're not going to talk about here, but you'll see analogs if you've seen those before. And these models really give you a way of structuring or thinking about how you write an algorithm. Right, so they are the random access machine and the primitive machine. So we'll start with random access machine. Okay, also known as the RAM. Can someone tell me what else RAM stands for? Yeah, random access memory. So this is both confusing but also convenient because RAM simultaneously stands for two things and they mean almost the same thing in one way. So I guess it's more confusing than useful, but there you go. So we have random access memory. Okay, that fits perfectly. And so we're thinking, this is random access memory is over here, the real computer land. That's like DRAM, SDRAM, whatever, things you buy, stick into your motherboard, or GPU, whatever. And over here, the mathematical analog of so here's RAM, here's also RAM, here's a random access machine, here's a random access memory. It's technical detail. But the idea is, if you look at RAM, that's in a computer, it's basically a giant array, right? You can go from 0 to, I don't know, typical chip these days, like 4 gigs in one thing. So you can go from 0 to 4 gigs, you can access anything in the middle there in constant time. To access something, you need to know where it is. That's random access memory. So that's an array. So I'll draw the picture, here's an array. Now, RAM is usually organized by words. So these are machine word, which we're going to put in this model. And then there's address 0, address 1, address 2, this is the fifth word, and just keep going. You can think of this as infinite, or the amount that you use, that's the space of the algorithm if you care about storage space. So that's basically it. Okay, now how do we, this is the memory side of things, how do we actually compute with it? It's very simple. We just say, in constant time, an algorithm can basically read in or load a constant number of words from memory, do a constant number of computations on them, and then write them out. It's usually called store. Okay, it needs to know where these words are. It accesses them by register, or sorry, by address. And so I guess constant number registers. Just hang around. So if you load some words into registers, you can do some computations on those registers, you can write them back, storing them in locations that are specified by registers. If you doesn't have assembly programming, this is what assembly programming is like. And you can see it can be rather annoying to write algorithms in this model, but in some sense it is reality. This is how we think about computers. If you're doing things like caches, this is an accurate model of computation. But loading, computing, and storing all take roughly the same amount of time, they'll take constant time. You can manipulate a whole word at a time. Now, what exactly is a word? Computers these days is like 32 bits or 64 bits, but we like to be a little bit more abstract. A word is W bits. It's slightly annoying, and most of this class we won't really worry about what W is. We'll assume that we're given as input a bunch of things which are words. So for example, peak finding, we're given a matrix of numbers. We didn't really say whether they're integers, floats, or what. We don't worry about that. We just think of them as words, and we assume that we can manipulate those words. In particular, given two numbers, we can compare them, which is bigger. And so we can determine, is this cell in the matrix a peak by comparing it with its neighbors in constant time. We didn't say why it was constant time to do that, but now you kind of know. If those things are all words, you can manipulate constant words in constant time. You can tell whether numbers are peak in constant time. You know some things like W should be at least log the size of memory, because a word should be able to specify an index into this array. And we might use that someday, but basically don't worry about it. Words are words. Words come in as inputs, you can manipulate them, and you don't have to worry about it. Okay? For the most part. In Unit 4 of this class, we're going to talk about what if we have really giant integers that don't fit in a word. How do we manipulate them? How do we add them, multiply them? So that's another topic. But most of this class, we'll just assume everything we're given is one word, and it's easy to compute on. Alright, so this is a realistic model, more or less, and it's a powerful one. But a lot of the time a lot of times you don't need arrays. Doesn't need it. Sometimes you need arrays, sometimes you don't. Sometimes you feel like not, sometimes you don't. So it's useful to think about somewhat more abstract models. They're not quite as powerful, but offer a simpler way of thinking about things. For example, this model will do dynamic memory allocation. You probably know you can implement dynamic memory allocation because real computers do it. But it's nice to think about a model that's taking care of it for you. It's kind of like a higher level programming abstraction. So the one that is useful in this class is Plan Machine. It basically corresponds to object-oriented programming in a simple, very simple version. So we have dynamically allocated objects. And an object has a constant number of fields. The field is going to be either a word, so you can think of this as, for example, storing an integer, one of the input objects, or something you computed on it, or a counter, all these sorts of things, or a pointer. And that's where pointing machine gets its name. A pointer is something that points to another object, or has a special value null, also known as nil, also known as none in Python. Okay, how many people have heard about pointers before? Who hasn't? Won't admit, only a few, that's good. Should have seen pointers. You may have heard them called references. Modern languages these days don't call them pointers because pointers are scary. But there's a very solid difference between them. This model actually really is references, but for whatever reason, called a pointer machine. Doesn't matter. The point is, you've seen linked lists, and linked lists have something, they have a bunch of fields in each node, so maybe you've got a pointer to the previous element, a pointer to the next element, and some value. So here's a very simple linked list. This is what we call a W linked list because it has previous and next pointers. So the next pointer points to this node, the previous pointer points to this node, next pointer points to null, the previous pointer points to null. So that's a two-node W linked list. You presumably have a pointer to the head of the list, maybe a pointer to the tail of the list, whatever. So this is a structure of the pointer machine, the data structure. In Python, you might call this a names tuple, or it's just an object with three attributes, it's called in Python. So here we have the value, that's a word, like an integer, and then some things can be pointers or pointer elements. And you can create a new node, you can destroy a node, that's the dynamic memory allocation. In this model, pointers or pointers, you can't touch them. Now, you can implement this model in a random access machine. A pointer becomes an index into this giant table. And that's more like pointers in C, if you've ever read C programs, because then you can take a pointer and you can add one to it, go to the next thing after that. In this model, you can just follow a pointer, that's all you do. Okay, following a pointer costs constant time, changing all these fields costs constant time. All the usual things you might imagine doing to these objects take constant time. So it's actually a weaker model than this one because you can implement a pointer machine in a random access machine. Okay, but it offers a different way of thinking. A lot of data structures are built this way. Cool. So that's the theory side. What I'd like to talk about next is, actually in Python, what's a reasonable model of what's going on? So these are old models. This goes back to the 80s. This one probably 80s or 70s. They've been around a long time. People use them. However, Python is obviously much more recent. At least modern versions of Python. And it's the model of computation in some sense in this class, because we're implementing everything in Python. And Python offers both a random access machine perspective because it has arrays, and it offers a pointer machine perspective because it has references, it has pointers. So you can do either one. But it also has a lot of operations. It doesn't just have load and store and follow pointer. It's got things like sort and append and concatenation of two lists and lots of things. And each of those have a cost associated with it. So whereas the random access machine and pointer machine, the theoretical models are designed to be super simple, so it's clear that everything you do takes constant time. In Python, some of the operations you can do take a lot of time. Some of the operations in Python take exponential time to do. You've got to know when you're writing your algorithms down, either thinking in a Python model or you're implementing your algorithms in actual Python, which operations are fast and which are slow. And that's what I'd like to spend the next few minutes on. There's a lot of operations, I'm not going to cover all of them, but we'll cover more in a station, and there's a whole bunch in my notes. I'll get all of them. So in Python, you can do random access style things. In Python, arrays are called lists, which is super confusing, but there you go. A list in Python is an array in real world. It's a super cool array, of course, but you can think of it as a list, but in terms of implementation, it's implemented as an array. Question? You thought Python lists were linked lists, that's why it's so confusing. In fact, they're not. In, say, C, back in the day, C, lists are linked lists. And it's very different. So when you do an operation here, you have a list L, and you do something like this. L is a list object. This takes constant time. In a linked list, it would take linear time. You've got to scan position I, scan position j, add 5, and so on. Okay, but in Python, this takes constant time. And that's important to know. I know the terminology is super confusing, but blame the development dictator for life. On the other hand, you can do style 2, pointer machine, using object-oriented programming. I'll just mention that there's I'm not really worrying about methods here. Methods are sort of a way of thinking about things, not super important from a cost standpoint. If your object has a constant number of attributes, you can't have like a million attributes, or can't have n attributes, then it fits into this pointer machine model. So if you have an object that only has like 3 things, 10 things, whatever, that's a pointer machine. You can think of manipulating an object as taking constant time. If you are messing around with the object dictionary doing lots of crazy things, then you have to be careful about whether this machine is true. But as long as you only have a reasonable number of attributes, this is all fair game. And so if you do something like, if you're implementing linked lists, Python and Checkstill does not have built-in linked lists. They're pretty easy to build though. You have a pointer and you say x equals x out next. That takes constant time because accessing this field in an object of constant size takes constant time. And we don't care what these constants are, that's the algorithm. So we only care about scalability of n. There's no n here. This takes constant time, this takes constant time. No matter how big your linked list is, or no matter how many objects you have, these are constant time. Okay, let's do some harder ones though. In general, the idea is if you take an operation like L.append, it's in the list, and you want to append some item to the list. It's an array though, so think about it. The way to figure out how much does this cost is to think about how it's implemented in terms of these basic operations. So these are sort of the core constant time things. Most everything can be reduced to thinking about this, but sometimes it's less obvious. Okay, L.append is a little tricky to think about because basically you have an array of some size, and now you want to make an array one larger. And the obvious way to do that is allocate a new array, copy all the elements. That would take linear time. Python doesn't do that. What does it do? Stay tuned for lecture 4. Okay. it does something called table doubling. It's a very simple idea. You can almost guess it from the title. And if you go to lecture, you'll see how this can basically be done in constant time. It's a slight catch, but basically think of it as a constant time operation. Once you have that, and so this is why you should take this class, so you'll understand how Python works. Okay, this is using an algorithmic concept that was invented, I don't know, decades ago, but it's a simple thing that we need to do to solve lots of other problems. So it's cool. There's a lot of features in Python that use algorithms, and that's kind of why I'm telling you. All right, so let's do another one, a little easier. What if I want to concatenate two lists? You should know in Python this is a non-destructive operation. You basically take a copy of L and L and concatenate them. Of course, they're arrays. The way to think about this is to re-implement it as Python code. This is the same thing as saying, well, L is initially empty, and then for every item x in L1, L.pen x. And a lot of the time in documentation for Python, you see this sort of here's what it means, especially in the fancier features. They give sort of an equivalent. Simple Python, if you will. It's not using fancy operations that we haven't seen already. So now we know this takes constant time, this append takes constant time, and so the amount of time here basically order the length of L1, and the time here is order length of L2, and so in total, it's order, I'm going to be careful and say 1 plus length of L1 plus length of L2. The 1 plus is just in case it's above 0, it still takes constant time to build initials. Okay, so there are a bunch of operations that are written in these notes. I'm not going to go through all of them because they're tedious, but if you just, a lot of them you just expand out code like this and it's very easy to analyze, whereas you just look at plus, you think, oh, plus is constant time. And plus is constant time if this is a word and this is a word, but these are entire data structures, and so it's not constant time. Alright? They're more so fun ones to think about, like, if I want to know is x in a list, how does that happen? In guesses, how you use there's an operator in Python called in, x in L. How long do you think this takes? Altogether? Linear, yeah. Linear time. In the worst case, you're going to have to scan through the whole list. Lists aren't necessarily sorted. You don't know anything about them. So you're going to just scan through and test for every item is x equal to that item. And it's even worse if equals costs a lot. So if x is some really complicated thing, you have to take that into account. Okay, blah, blah, blah. Okay, another fun one. This is like a pop quiz. How long does it take to complete the length list? Constant. Yeah, luckily, if you didn't know anything, you have to scan through the list and like count the items. But in Python, lists are implemented with a counter built in. It always stores the list at the beginning. Stores the length of the list at the beginning, so you just look it up. This is instantaneous. It's important though. That can matter. All right, let's do some more. What if I want to sort of it? How long does that take? N log n. Where n is the length of the list. Technically times the time to compare two items. But usually we're just sorting words. If you look at Python sorting algorithm, using the comparison sort. This is the topic of lectures 3 and 4 and 7. In particular, the very next lecture, we will see how it's done in N log n time. Okay, and that's using algorithms. All right, let's go to dictionaries. Python called dicts. And here's what you do in generalization list in some sense. Instead of putting just an index here, an integer, from 0 on the length -1, you can put an arbitrary key and sort value. How does this take? In fact, this is one of the most important data structures in computer science. It's called hash table, and it is the topic of lectures 8 through 10. So stay tuned for how to do this in constant time. How to be able to sort arbitrary key, get it back out in constant time. This is assuming the key is a single word. Okay. Yeah, it will corroborate an existing key. There's also, you can test whether key is in the dictionary. That also takes constant time. You can delete something from the dictionary. All the usual dealing with a single key in dictionaries. Obviously, dictionary to update that involves a lot of keys. That doesn't take constant time. How long does it take? Well, you write out for loop. How do you do this in constant time? Come to lecture 8 through 10. I should say a slight catch, which is this is constant time with high probability. The randomized algorithm. It doesn't always take constant time, so it's correct. But sometimes, very rarely, it takes a little more than constant time. I'm going to abbreviate this WHP. And we'll see more what that means. Mostly I say 6046, but we'll see a fair amount in 6046 on how this works and how it's possible. It's a big area of research. A lot of people work in hashing. It's very cool. And it's super useful. If you're in any code these days, use the dictionary. It's the way to solve problems. I'm basically using Python as a platform to advertise the rest of the class. You can not every topic we cover in this class is already in Python, but a lot of them are. So we've got table doubling, we've got dictionaries, we've got sorting. Another one is longs, which are long integers in Python 3.2. And this is the topic of lecture 11. And so for fun, if I have two integers x and y, and let's say one of them is this many words long, and the other one is this many words long, how long do you think it takes to add them? Plus times plus. You can do that much time. If you think about the graceful algorithm for adding really big multi-digit numbers, it'll take that much time. Well, it takes a little bit harder though. You look at the graceful algorithm, it's going to be x times y. Quadratic time, not so good. The algorithm that's implemented in Python is x plus y to the log base 2 of 3. By the way, I always write LG to mean log base 2. Because I have 2 bases 2. Log base 2 of 3 is about 1.6. So while the straightforward algorithm is basically x plus y squared, this one is x plus y to the 1.6 power, a little better than quadratic. And Python found that was the Python developers found that was faster than graceful multiplication, and so that's what they implemented, and that's something we'll cover in lecture 11, how to do that. It's pretty cool. There are faster algorithms, but this is one that works quite practically. One more. Heap cube. This is in the Python standard library, and implement something called heap, which will be in lecture 4. So coming soon to a classroom review. Okay, enough advertisement. That gives you some idea of the model of computation. There's a whole bunch more in these notes which are online. Go check them out. And some of them we'll cover in station tomorrow. I'd like to now that we are sort of comfortable with what in Python, I want to do a real example. And so last time we did find me, we're going to have another example which is called document distance. So let's do that. Any questions before we go on? So, document distance problem is I give you two documents, I'll call them D1 and D2, and I want to give you the distance between them. And the first question is, what does that mean? What is this distance function? Okay, let me first tell you some motivations for computing document distance. Let's say you're Google and you're cataloging the entire web. You'd like to know when two web pages are basically identical because then you store less. And because you present differently to the user, you say, well, there's this page and there's lots of extra copies, so just here's the commodity. Or you're Wikipedia, and if you're looking at Wikipedia, there's a list of all your Wikipedias, like millions of them, and they find them by hand, but you could do that using document distance. Say, are these basically identical other than like some stuff that jump at the beginning of the hand. Or if you're teaching this class and you want to check out performance test okay, identical, we do this a lot. I'm not going to tell you what this function uses, so to take the point, it's not the one we covered in class, but we use automated test for whether you're cheating. Doesn't work. Let's search. Let's say Google again, and you want to implement searching. Like I give you 3 words, I'm searching for introduction to algorithms. You can think of this algorithm as a very short document, and you want to test whether that document is similar to all the other documents anyway. And one is similar, one has a small distance, that's maybe what you want to do. That's obviously not what you do, that's part of the test. So that's why you might care. It's part of the also problem that let's illustrate a lot of things that we develop in this class. Alright, I'm going to think of a document as a sequence of words. This will be a little formal, what do I mean by document? And a word, which is going to be a string of alphanumeric characters. Okay, A through Z and 0 through 9. Okay, so if I have a document which you also need as a string, and you basically delete all the white space and punctuation and all the other junk that's in there, just everything between those are the words. Okay, that's a simple definition of equal documents words. And now we can think about, well, if I want to know whether each are similar, I've thought about my document as a collection of words. Maybe they're similar if they share a lot of words in common. So that's the idea. Look at shared words. And use that to define documents. This is obviously only one way to define distance. It'll be the way to do it in this class, but there are lots of other possibilities. So I'm going to think of a document. This is words, but I can also think of it as a vector. So if I have a document D and I have a word W, this D of W is going to be the number of times that word occurs in the document. So the number of occurrences of W in document D. So it's a number, it's an integer, non-negative integer. Could be 0, could be 1, could be a million. Okay, I think of this as a giant vector. The vector is indexed by all words. And for each of them, there's some frequency, one of them is 0, and then some of them have some positive number of occurrences. Okay, you can think of every document as being one of these plots in this common axis. So there's infinitely many words down here, so it's kind of a big axis, but it's one way to draw a picture. Okay, so for example, take two very important documents. Everybody likes cats and dogs. So these are two word documents, and so we can draw them, because there's only 3 different words here, we can draw them in 3-dimensional space. Beyond that, it's a little hard to draw. So we have, let's say this one's the, it's easier to draw. So there's going to be just 0 here and 1, which the axes, and say this is dog, and this is cat. Okay, so the cat has one the, it has one cat and no dog, so it's here. It's a vector pointing there. The dog, you've got, it's pointing there. Okay, so these are 2 vectors. So how do I measure how different 2 vectors are? Any suggestions from vector calculus? Inner product? Yeah, that's a good suggestion. Any others? Okay, we'll go with inner product. I like inner product. Also known as dot product. Find it quickly. So we could, I'm going to call this B prime, this is not what we're going to end up with. We can do this as the dot product of B1 and B2, also known as the sum over all words of B1 of W times B2 of W. Okay, so for example, we take the dot product of these two guys, the those match, so you get 1 point there, cat and dog multiplied by 0, so you don't get much there. So this is some measure of distance, but it's a measure of actually a commonality, so these are inverse distance there. If you have a high dot product, you have a lot of things in common, because a lot of these things wasn't 0 times something. It's actually a positive number times a positive number. You have a lot of shared words, then that looks good. The trouble with this is that if I have a long document, say a million words, and it's 99% in common with another document that's a million words long. It's still, it looks super similar, actually. Let's say it's a million words long, half of the words are in common. So not that many, but a fair number. Then I have a score of like 500,000. And then I have 2 documents which say are 100 words long, and they're identical. Their score is maybe only 100. So even though they're identical, it's not quite scaling down. It's not quite a perfect measure. And you can just try to fix this. This I think is a little tricky, okay? Divide by length of vectors. I think that's what we're and then we close, yeah. Sorry. So, divide by length of vectors. And obviously double prime. Still not quite the right answer. Right now, pretty good. Okay. So here the length of the vectors is the number of words that occur. This is pretty cool, but does anyone recognize this formula? Angle, yeah. It's a lot like the angle between 2 vectors. It's just off by an arc cos. This is the cosine of the angle between 2 vectors. And I'm a geometry, I like geometry, so if you take arc cos of that thing, that's a well-established distance vector. This goes back to 75. You can do it. But people early days of document information retrieval, way before web, people are still working on this stuff. So it's an actual measure of the angle between 2 vectors. If it's 0, they're basically identical. If it's 90 degrees, they're really, really different. And so that gives you a nice way to keep document. The question is, how do we actually compute that measure? Now that we've come up with something that's reasonable, how do I actually find this value? I need to compute these vectors, the number of occurrences of each word in the document, and I need to compute the dot product, and then I need to divide. That's really easy. So dot product, I also need to decompose the document into those words. So there are 3 things I need to do. Let me write that down. Those are the algorithm. 1, split a document into words. Second is compute word frequencies. How many times each word appears? This is the document vectors. And then the third step is to compute the dot product. Let me tell you a little bit about how each of those is done. Some of these will be covered more in future lectures. I'm going to give you an overview. There's a lot of ways to do each of these steps. If you look at the next to the lecture notes for this, lecture 2, there's a bunch of code and a bunch of data examples of documents, big corpuses of text. And you can run, I think there are 8 different algorithms for it. And let me give you, actually, I cut the chase a little bit and tell you about the runtimes of these different implementations of this same algorithm. There are lots of versions of this algorithm implemented a whole bunch. Every semester I teach this, I change a little bit more, add a few more variants. So version 1, on a particular pair of documents, which is like a megabyte, very much text. It takes 228.1 seconds. Super slow. Pathetic. Then we do a little bit of algorithm tweaking. We get down to 164 seconds. Then we get to 123 seconds. Then we get down to 71 seconds. Then we get down to 18.3 seconds. Then we get to 11.5 seconds. Then we get to 1.8 seconds. Then we get to 0.2 seconds. So factor of 1,000. This is just in Python. 2/10 of a second plus the megabytes. All right, it's getting reasonable. This is not so reasonable. Some of these improvements are algorithmic. Some of them are just better coding. So there's, I think, improving constant factors. But as you, if you look at larger and larger text, this will become even more dramatic because a lot of these were improvements from quadratic time algorithms to linear and log n algorithms. And so for a megabyte, yeah, it's reasonable. Like a gigabyte would be a huge improvement. But we know comparison effect. We know comparisons. This one will never finish. So the reason I ran such a small example so I can have patience to wait for this one. But this one you can run on the bigger examples. All right. So where am I going from here? 5 minutes. I'm going to tell you about some of those improvements and some of the algorithms here. Let's start with this very simple one. How would you split a document into words in Python? Yeah. Iterate through that's actually how we do number 2. Okay, we can talk about that one. Iterate through the words in the document and put it in a dictionary. Let's say count word plus equals 1. This would work if count is something called count dictionary if you're super Pythonista. Otherwise, you have to check is the word in the dictionary. If not, set it to 1. If it is there, add 1. Okay, but I think you know what this means. This will count the number of words. This will count the frequency of each word in the dictionary. And because dictionaries run in constant time with high probability, this will take order. Well, actually a little bit. Because words can be really long, so to reduce a word down to a machine word could take order the length of the word. Maybe a little more precise. This is going to be the sum of the lengths of the words in the document, which is also known as the length of the document. This one. This is good. This is linear time with high probability. Okay, that's a good algorithm. That is introduced in algorithm 4. So we got a significant boost. There are other ways to do this. For example, you can sort the words and then run through the sorted list and count how many you get in a row for each one. If it's sorted, you can count. All the identical words are put right next to each other, so it's easy to count them. And that'll run almost as fast. That was one of these algorithms. Okay, so that's a couple different ways to do that. Let's go back to this first step. How would you split a document into words in the first place? Yeah. So run through the string, and every time you see anything that's not alphanumeric, start a new word. And that will run in linear time. That's a good answer. So it's not hard. If you're a fancy Pythonista, you might do it like this. Remember my regex is? and this will find all the words in the document. Trouble is, in general, RE takes exponential time. So if you think about algorithms, be very careful. Unless you know how RE is implemented, this probably will run in linear time. But if it's not obvious at all, do anything fancy with regular expressions. You don't know this means, don't worry about it. Don't use it. Okay? If you know about it, be very careful not to use RE because it's not always linear time. Okay, but there's an easy algorithm for this, which is just scan through and look for alphanumerics. String them together. It's good. There's a few other algorithms you're going to notice, you should check them out. And for fun, look at this code and see how small differences make dramatic differences in performance. Next class will be about sorting.
The following content is provided under a Creative Commons license. Your support will help MIT Open Courseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT Open Courseware at ocw.mit.edu.
So today's lecture is on sorting. We'll be talking about specific sorting algorithms today. I want to start by motivating why we're interested in sorting, which will be fairly easy. And then I want to discuss a particular sorting algorithm, the probably searching sort. That's probably the simplest sorting algorithm you can write. It's 5 lines of code. It's not the best sorting algorithm that's out there, and so we try and improve it. And we'll also talk about merge sort, which is a divide and conquer algorithm. And that's going to motivate the last thing that I want to spend time on, which is recurrences and how you solve recurrences. And typically, the recurrences that you'll be looking at in 006 are going to come from divide and conquer problems, like merge sort, but you'll see this over and over. So let's talk about why we're interested in sorting. Now, there's some fairly obvious applications. Like, if you want to make it a phone book, you've got a bunch of names and numbers corresponding to a telephone directory. You want to keep them sorted order so it's easy to search, MP3 organizers, spreadsheets, etc. So there's lots of obvious applications. There's also some interesting problems that become easy once items are sorted. And one example of that is finding a median, for example. So let's say that you have a bunch of items in an array, A0 through N, and A0 through N contain N numbers, and they're not sorted. When you sort, you turn this into B0 through N, where you may sort them in increasing order or decreasing order. This is for now, and order the records, and they're not numbers. Then you have to provide a comparison function to determine which record is smaller than another record, and that's another input that you have in order to do the sorting. So it doesn't really matter what the items are, as long as you have a comparison function, think of it as less than or equal to, and if you have that, and it's straightforward, you obviously check the 3 is less than 4, etc. But maybe a little more complicated for more sophisticated sorting applications. The bottom line is that if you have your algorithm that takes a comparison function as an input, you're going to be able to go on a certain amount of time, get B0n. Now, if you want to find the median of the set of numbers that were originally in the array A, what would you do once you have a sorted array B? Yeah. Oh, absolutely. But there's this is sort of a side effect of having a sorted list. If you happen to have a sorted list, there's many ways that you could imagine building up a sorted list. One way is you have something that's completely unsorted and you run insertion sort or merge sort. Another way would be to maintain a sorted list as you're getting items put into the list. Okay, so if you happen to have a sorted list and you need to have a sorted list for some reason, at the point I'm thinking here is that finding the median is easy. Okay, and it's easy because all you have to do is you go look at depending on whether n is odd or even, and look at b of n over 2. Right, that would give you the median because you have a bunch of numbers that are less than that and the equal set of numbers that are greater than that, which is the definition of median. All right, so this is not necessarily the best way, as you pointed out, of finding the median, but it's constant time if you have a sorted list. Right, that's the point I want to make. The other thing that you can do, and this came up in Eric's lecture, which is the notion of binary search. Finding an element in an array, a specific element. You have a list of items again, A0 through N, and you're looking for a specific number or item. You can obviously scan the array, and that will take you linear time to find this item. If the array has to be sorted, then you can find this in logarithmic time using what's called binary search. Okay? And binary search, let's say you're looking for a specific item, let's call it K. Binary search, roughly speaking, would work like you go compare K to, again, B of N over 2, and decide if that B is sorted, you get to look at one half of the array. If B of N over 2 is not exactly K, then by the time K you're done, otherwise you look at the left half, you do a divide and conquer paradigm, and you do this in logarithmic time. So keep this in mind because binary search is going to come up in today's lecture and again in other lectures. It's really a great paradigm of divide and conquer, probably the simplest, and it essentially takes something that's linear search and turns it into logarithmic search. So those are a couple of problems that become easy if you have a sorted list. And there's some not so obvious applications of sorting. For example, data compression. If you want to compress a file, one of the things that you could do is to, and it's a set of items, you could sort the items, and that automatically finds duplicates. And you can say, if I have 100 items that are all identical, I'm going to why? You pointed out the finding median, but it's constant time if you have a sorted list. Right? That's the point I want to make. The other thing that you can do, and this came up in Eric's lecture, which is the notion of binary search. Finding an element in an array, a specific element. You have a list of items, again, A0 through N, and you're looking for a specific number or item. You could obviously scan the array, and that would take you a long time to find this item. If the array happened to be sorted, then you can find this in logarithmic time using what's called binary search. Okay? And binary search, let's say you're looking for a specific item, let's call it K. Binary search, roughly speaking, would work like you go compare K to, again, B of N over 2, and decide, given that B is sorted, you get to look at one half of the array. If B of N over 2 is not exactly K, then, well, if it's exactly K, you're done. Otherwise, you look at the left half, you do your divide and conquer paradigm, and you can do this in logarithmic time. All right? So keep this in mind because binary search is going to come up in today's lecture and again in other lectures. It's really a great paradigm of divide and conquer, probably the simplest, and it essentially takes something that's linear, the linear search, and turns it into logarithmic search. So those are a couple of problems that become easy if you have a sorted list, and there's some not so obvious applications of sorting. For example, data compression. If you wanted to compress a file, one of the things that you could do is to, and it's a set of items. You could sort the items, and that automatically finds duplicates. And you could say, if I have 100 items that are all identical, I'm going to compress the file by representing the item once, and then having a number associated with the frequency of that item. Similar to what document distance does. Document distance can be viewed as a way of compressing your initial input. Obviously, you lose the works of Shakespeare or whatever it was, and it becomes a bunch of words and frequencies. But it is something that compresses the input and gives you a different representation. And so people use sorting as a subroutine in data compression. Computer graphics uses sorting. Most of the time, when you render scenes in computer graphics, you have many layers according to the scene. It turns out that in computer graphics, most of the time you're actually rendering front to back, because when you have a big opaque object in front, you want to render that first, so you don't have to worry about everything that's occluded by this big opaque object, and that makes things more efficient. And so you keep things sorted front to back most of the time in computer graphics rendering. But some of the time, if you're worried about transparency, you have to render things back to front. So typically you have sorted lists corresponding to the different objects in both orders, both increasing order and decreasing order, and you're maintaining that. So sorting is a real important subroutine in pretty much any sophisticated application you look at. So it's worthwhile to look at the variety of sorting algorithms that are out there. And we're going to do some simple ones today. But if you go look at Wikipedia and do a Google search, there's all sorts of sorts like cocktail sort and Pythonic sort and what have you. And there's reasons why each of these sorting algorithms exist, because in specific cases they end up winning on types of inputs or types of problems. All right. So let's take a look at our first sorting algorithm. I'm not going to write code, but it will be in the notes, and it is in your document distance Python files. But I'll just give you a pseudocode here and walk through what insertion sort looks like, because the purpose of really describing this algorithm to you is to analyze its complexity. We need to do some counting here with respect to this algorithm to figure out how fast it's not running and what the worst case complexity is. So what is insertion sort? For I equals 1, 2 through n, given an input to be sorted, what we're going to do is we're going to insert a of I in the right position, and we're going to assume that we are sort of midway through the sorting process, where we have sorted A0 through I minus 1, and we're going to expand this array to have I plus 1 elements, and A of I is going to get inserted into the correct position. And we're going to do this by pairwise swaps down to the correct position for the number that is initially in A of I. All right, so let's go through an example of this. You're going to sort in increasing order. Just have 6 numbers. And initially you have 5, 2, 4, 6, 1, 3. And you're going to take a look at this, and you start with the index 1 or the second element, because the very first element, it's a single element and it's already sorted by definition. But you start from here, and this is what we call our key. And that's essentially a pointer to where we're at right now, and the key keeps moving to the right as we go through the different steps of the algorithm. And so what you do is you look at this, and you have, this is A of I, that's your key, and you have A of 0 to 0, which is 5. And this, since we want to sort in increasing order, this is not sorted, and so we do a swap. So what this would do in this step is to do a swap, and we would go obtain 2, 5, 4, 6, 1, 3. So all that's happened here in this step, in the very first step where the key is in the second position, is one swap happened. Now your key is here at item 4. Again, you need to put 4 into the right spot, and so you do pairwise swaps. And in this case, you have to do one swap, and you get 2, 4, 5, and you're done with this iteration. So what happens here is you have 2, 4, 5, 6, 1, 3, and now the key is over here at 6. Now at this point, things are kind of easy, in the sense that you look at it and you say, well, 6 is, I know that this part is already sorted, 6 is greater than 5, so you have to do nothing. So there's no swaps that happen in this step. So all that happens here is you're going to move the key to one step to the right. So you have 2, 4, 5, 6, 1, 3, and your key is now at 1. Here you have to do more work. Now you see one aspect of the complexity of this algorithm, given that you're doing pairwise swaps. The way this algorithm was defined in pseudocode out there was, I'm going to use pairwise swaps to find the correct position. So what you're going to do is you're going to have to swap first 1 and 6, and then you'll swap, 1 is over here, so you'll swap this position and that position, and then you'll swap, essentially do 4 swaps to get to the point where you have 1, 2, 4, 5, 6, 3. So this is the result. 1, 2, 4, 5, 6, 3. And the important thing to understand here is that you've done 4 swaps to get one to the correct position. Now you can imagine a different data structure where you move this over there and you shift them all to the right, but in fact that shifting of these 4 elements is going to be computed in our model as 4 operations, or 4 steps anyway. So there's no getting away from the fact that you have to do 4 things here, and the way insertion sort, of the code that we have for insertion sort does this is by using pairwise swaps. So we're almost done. Now we have the key at 3, and now 3 needs to get put into the correct position, and so you've got to do a few swaps. This is the last step. And what happens here is 3 is going to get swapped with 6, and then 3 needs to get swapped with 5, and then 3 needs to get swapped with 4, and then since 3 is greater than 2, you're done. So 1, 2, 3, 4, 5, 6. And that's it. So, analysis. How many steps do I have? Yep. How many steps do I have? I guess that wasn't a good question. If I think of a step as being a movement of the key, how many steps do I have? I have theta n steps, and in this case you can think of it as n minus 1 steps since you started with 2. But let's just call it theta n steps in terms of key positions. And you're right, it is n squared, because at any given step, it's quite possible that I have to do theta n work. And one example is this one right here, where I had to do 4 swaps. And in general, you can construct a scenario where towards the end of the algorithm, you'd have to do theta n work. But if you had a list that was reverse sorted, you would essentially have to do, on an average, n by 2 swaps as you go through each of the steps, and that's theta n. So each step is theta n swaps. Okay? And when I say swaps, I could also say each step is theta n compares and swaps. All right? And this is going to be important because I'm going to ask you an interesting question in a minute. But let me summarize. What I have here is a theta n square algorithm. The reason this is a theta n square algorithm is because I have theta n steps, and each step is theta n. When I'm counting, what am I counting in terms of operations? The assumption here, unspoken assumption, is being that an operation is a compare and a swap, and they're essentially equal in cost. Okay? And in most computers, that's true. You have a single instruction in, say, the x86 or the mesh architecture that can do a compare, and the same thing for swapping registers. So, perfectly reasonable assumption that compares and swaps for numbers have exactly the same cost. But if you had a record and you were comparing records, and the comparison function that you use for the records was in itself a method call or a subroutine, it's quite possible that all you're doing is swapping pointers or references to do the swap, but the comparison could be substantially more expensive. Okay? For most of the time, and we'll differentiate if it becomes necessary, we're going to be counting comparisons in the sorting algorithms that we'll be putting up. And we'll be assuming that either compares and swaps are roughly the same, or that compares are, and we'll say which one, of course, all that compares are substantially more expensive than swaps. Okay, so if you had either of those cases for inserting sorts, you have a theta n squared algorithm. Right? You have theta n squared compares and theta n squared swaps. Now, here's the question. Let's say that compares are more expensive than swaps. And so I'm concerned about the theta n squared comparison cost. I'm not as concerned because of the constant factors involved with the theta n squared swap cost. All right? What's the simple? This is a Christian question. Okay, what's a simple fix, change to this algorithm that would give me a better complexity in the case where compares are more expensive, or I'm only looking at the complexity of compares, so the theta whatever of compares. Anyone? Yeah, right there. If you compare with the what did I call it? I called it something. What you just said, I called it something. Yeah, I saw you first. Binary search, that's right. 2 questions for this one. All right, so you pick them up after lecture. So you're exactly right. You got it right. I called it binary search up here. Okay, and so if you take insertion sort and you can sort of trivially turn it into a theta n log n algorithm if you're talking about n being the number of compares. Okay, and all you have to do that is to say, you know what, I'm going to replace this with binary search, and you can do that. And that was the key observation. That because a of 0 through I minus 1 is already sorted, right? And so you can do binary search on that part of the array. And so let me just write that down. Do a binary search on a of 0 through I minus 1, which is already sorted. And essentially, you can think of it as theta log I time, and for each of those steps, and so then you get your theta n log n. But Okay, now why can't I theta log n in terms of compares? Does this help the swaps for an array data structure? No, because binary search will require insertion into A of 0 through I minus 1, right? So here's the problem. Why don't we have a full-fledged theta n log n algorithm regardless of the cost of compares or swaps? We don't quite have that, right? We don't quite have that because we need to insert our A of I into the right position into A of 0 to I minus 1. When you do that, if you have an array structure, you might get into the middle and you have to shift things over to the right. And when you shift things over to the right, in the worst case, you may be shifting a lot of things over to the right, and that gives back to worst case complexity of theta n. Okay? So a binary search in insertion sort gives you theta n log n for compares, but it's still theta n squared for swaps. All right? Okay, good. So as you can see, there's many varieties of sorting algorithms. We just looked at a couple of them. And they're both insertion sort. The second one that I just put up is, I guess, technically called binary insertion sort because it does binary search. And the vanilla insertion sort is the one that we have the code for in the docdist program. It is one of the docdist files. So let's move on and talk about a different algorithm. So what we'd like to do now, this class is about constant improvement, right? You're never happy. We always want to do a little bit better, right? And eventually, once we run out of room from an asymptotic standpoint, you take these other classes where you try and improve constant factors and get 10% and 5% and 1% and so on and so forth. But we'll stick to improving asymptotic complexity, and we're not quite happy with binary insertion sort because in the case of numbers, our binary insertion sort has theta n square complexity if you look at swaps, right? So we'd like to go find an algorithm that is theta n log n, and then I guess eventually we'll have to stop, but Eric will take care of that. There's a reason to stop. It's when you can prove that you can't do any better, right? And so we get to that eventually. So merge sort is also something that you've probably seen, but there'll probably be a couple of summaries that come out as I describe this algorithm that hopefully will be interesting to those of you who already know merge sort. And for those of you who don't, it's a very pretty algorithm. It's a standard recursive algorithm, similar to a binary search. What we do here is we have an array A. We split it into two parts, L and R. And essentially, we kind of do no work really in terms of the L and R in the sense that we keep splitting, and all the work is done down at the bottom in this routine called merge, where we are merging a pair of elements at the leaves, and then we merge two pairs and get 4 elements, and then we merge 4 tuples of elements, etc., and go all the way up. So what I'm saying L turns into L prime out here, there's no real explicit code, but you can see that turns L into L prime. It happens really later. There's no real sorting code here. It happens in the merge routine, and you'll see that quite clearly when we run through an example. So you have L and R turn into L prime and L prime and R prime, and what we end up getting is a sorted array A, and we have what's called a merge routine that takes L prime and R prime and merges them into the sorted array. So at the top level, what you see is split into 2 and do a merge and get to the sorted array. The input is of size n. You have 2 arrays of size n over 2. These are 2 sorted arrays of size n over 2. And then finally you have a sorted array of size n. So if you want to follow the recursive execution of this in a small example, then you'll be able to see how this works. And we'll do a fairly straightforward example with 8 elements. So at the top level, before we get there, merge is going to assume that you have 2 sorted arrays and merge them together. That's the invariant in merge sort, or for the merge routine. It assumes the inputs are sorted, L and R, but it's actually, I should say, L prime and R prime. So let's say you have 20, 13, 7, and 2. You have 12, 11, 9, and 1. And this could be L prime, and this could be R prime. What you have is what we call a 2-finger algorithm. And so you got 2 fingers, and each of them point to something. And in this case, one of them is pointing to L. My left finger is pointing to L prime, or some element in L prime. My right finger is pointing to some element in R prime. And I'm going to compare the 2 elements that my fingers are pointing to. And I'm going to choose, in this case, the smaller of those elements. And I'm going to put them into the sorted array. Okay, so start out here. I look at that, and I compare 2 and 1. And which is smaller? 1 is smaller. So I'm going to write 1 down. This is a 2-finger algo for merge. And I put 1 down. When I put 1 down, I have to cross out 1. So effectively what happens is, let me just circle that instead of crossing it out, and my finger moves up to 9. Okay, so now I'm pointing at 2 and 9, and I repeat this step. Right, so now in this case 2 is smaller, so I'm going to go ahead and write 2 down, and I can cross out 2 and move my finger up to 7. All right, and so that's it. I won't bore you with the rest of the steps. It's essentially walking up. You have a couple of pointers, and you're walking up these two arrays, and you're writing down 1, 2, 7, 9, 11, 12, 13, 20. Okay? And that's your merge routine. And all of the work really is done in the merge routine, because other than that, the body is simply a recursive call. I mean, you have to obviously split the array, but that's fairly straightforward. If you have an array, and this could be R prime, what you have is what we call a two-finger algorithm. And so you got two fingers, and each of them point to something. And in this case, one of them is pointing to L. My left finger is pointing to L prime, or some element in L prime. My right finger is pointing to some element in R prime. And I'm going to compare the two elements that my fingers are pointing to, and I'm going to choose, in this case, the smaller of those elements, and I'm going to put them into the sorted array. Okay, so start out here. I look at that, and I compare 2 and 1, and which is smaller? 1 is smaller. So I'm going to write 1 down. This is a two-finger algorithm for merge, and I put 1 down. When I put 1 down, I have to cross out 1. So effectively, what happens is, let me just circle that instead of crossing it out, and my finger moves up to 9. Okay, so now I'm pointing at 2 and 9, and I repeat this step. Right? So now in this case, 2 is smaller, so I'm going to go ahead and write 2 down, and I can cross out 2 and move my finger up to 7. All right? And so that's it. I won't bore you with the rest of the steps. It's essentially walking up. You have a couple of pointers, and you're walking up these two arrays, and you're writing down 1, 2, 7, 9, 11, 12, 13, 20. Okay? And that's your merge routine. And all of the work really is done in the merge routine, because other than that, the body is simply a recursive call. I mean, you have to obviously split the array, but that's fairly straightforward. If you have an array, A 0 through n, then depending on whether n is odd or even, you can imagine that you set L, to be A 0 n by 2 minus 1, and R similarly. And so you just split it halfway in the middle, and I'll talk about that a little bit more. There's a subtlety associated with that we'll get to in a few minutes. But to finish up in terms of the computation of merge sort, this is it. The merge routine is doing most, if not all, of the work, and this two-finger algorithm is going to be able to take two sorted arrays and put them into a single sorted array by interspersing or interleaving these elements. And what's the complexity of merge? If I have two arrays of size n over 2 here, what do I have? Yeah, n. All right, we'll give you a question too. Theta n complexity. So far so good. It's a little, I know you know the answer as to what the complexity of merge sort is, but I'm guessing that most of you won't be able to prove it to me, because I'm kind of a hard guy to prove something to. Anyway, and I can always say no, I don't believe you, or I don't understand, right? So it's the complexity, and you've said this before in class, and I think Eric's mentioned it. The overall complexity of this algorithm is theta n log n. Okay, and where does that come from? How do you prove that? And so what we do now is take a look at merge sort, and we'll look at a recursion tree. We're trying, there are many ways of proving that merge sort is theta n log n. The way we're going to do this is what's called proof by picture. And it's not an established proof technique, but it's something that is very helpful to get an intuition behind the proof and why the result is true. Right? So, and you can always take that and you can formalize it and make this something that everyone believes. And you can also look at substitution possibly in section tomorrow for recurrence solving. So where we're at right now is that we have a divide and conquer algorithm that has a merge step that is theta n. And so if I just look at this structure that I have here, I can write a recurrence for merge sort that looks like this. When I say complexity, I can say T of n, which is the work done for n items, is going to be some constant time in order to divide the array. So this would be the part corresponding to dividing the array. And there's going to be two problems of size n over 2. And so I have 2t of n over 2. And this is the recursive part. And I'm going to have c times n, which is the merge part. Okay? And that's some constant times n, which is what we have here with respect to the theta n complexity. So you have a recurrence like this, and I know some of you have seen recurrences in 6 over 2, and you know how to solve this. What I'd like to do is show you this recursion tree expansion that not only tells you how to solve this recurrence, but also gives you a means of solving recurrences where instead of having c of n, you have something else out here. You have f of n, which is a different function from the linear function. And this recursion tree is, in my mind, the simplest way of arguing the theta n log n complexity of merge sort. Right, so what I'm going to do is expand this recurrence out, and let's do that over here. So I have c of n on top. I'm going to ignore this constant factor because c of n dominates. So I just start with c of n. I want to break things up as I do the recursion. So when I go c of n at the top level, that's the work I have to do at the merge at the top level. And then when I go down to two smaller problems, each of them is size n over 2, so I do c times n, divided by 2 work. So this is just a constant c. It just represents, I don't want to write thetas up here, you could. And let's say a little bit more about that later, but think of this Cn as representing the theta n complexity, and C is this constant. So C times n here, C times n over 2 here, and then when I keep going, I have C times n over 4, C times n over 4, etc., and so on and so forth. And when I come down all the way here, n is eventually going to become 1, or essentially a constant, and I'm going to have a bunch of C's here. All right? So here's another question that I'd like you to answer. Someone tell me what the number of levels in this tree are precisely, and the number of leaves in this tree are precisely. Yeah. Log n plus 1, log to the base 2 plus 1. Yeah, and the number of leaves? Yeah, you raise your hand back there first. Number of leaves. Yeah, you're right. You think right. Okay, so 1 plus log n and n leaves. All right, when n becomes 1, you know, how many of them do you have? You're down to a single element, which is by definition sorted, and you have n leaves. Right, so now let's add up the work. Right, so this is, I really like this picture because it's just so intuitive in terms of getting us the result that we're looking for. Right, so you add up the work in each of the levels of this tree. All right, so the top level is Cn, the second level is Cn because I added half and half. Cn, wow, what's symmetry? Okay, so you're doing the same amount of work, modulo the constant factors here, but what's going on with the C1, which we've ignored, but roughly the same amount of work in each of the levels, right? And now you know how many levels there are. It's 1 plus log n. So if you want to write an equation for T of n, it's 1 plus log n times C of n, which is theta of n log n. All right. So I've mixed in constant C and thetas. They're, for the purposes of this description, they're interchangeable. You will see recurrences that look like this in class, and things like that. Don't get confused. It's just a constant multiplicative factor in front of the function that you have. And it's just a little easier, I think, to write down these constant factors and realize that the amount of work done is the same in each of the leaves. And once you know the dimensions of this tree in terms of levels and in terms of the number of leaves, you get your result. All right. So we've looked at two algorithms so far. And insertion sort, if you talk about numbers, is theta n squared for swaps. Merge sort is theta n log n. Here's another interesting question. What is one advantage of insertion sort over merge sort? Yeah. What does that mean? That's exactly right. That's exactly right. So the two guys who answered the questions before, but the levels and you, come to me after class. So that's a great answer. It's in-place sorting is something that has to do with auxiliary space. And so what you see here, and it was a bit hidden here, but the fact of the matter is that you had L prime and R prime, and L prime and R prime are different from L and R, which were the initial halves of the inputs to the sorting algorithm, right? And what I said here is, you're going to dump this into A. That's what this picture shows. This says sorted array A. And so you have to make a copy of the array, the two halves L and R, in order to do the recursion, and then to take the results and put them into the sorted array A. So you needed, in merge sort, you needed theta n auxiliary space. So merge sort, you need theta n extra space, and the definition of in-place sorting implies that you have theta 1 constant auxiliary space. Okay? The auxiliary space for insertion sort is simply that temporary variable that you need when you swap two elements. Right? So when you want to swap a couple of registers, you got to store one of the values in a temporary location, override the other, etc. And that's the theta 1 auxiliary space for insertion sort. So there is an advantage of the version of insertion sort we've talked about today over merge sort. And if you have a billion elements, that's potentially something you don't want to store in memory. If you want to do something really fast and do everything in cache or main memory, and you want to sort billions or maybe even trillions of items, this becomes an important consideration. I will say that you can reduce the constant factor of the theta n. So in the vanilla scheme, you can imagine that you have to have a copy of the array. So if you had n elements, you essentially have n extra items of storage. You can make that n over 2 with a simple coding trick by keeping one half of A. You can sort of throw away one of the L's or one of the R's, and you can get it down to n over 2. And that turns out it's a reasonable thing to do if you have a billion elements and you want to reduce your storage by a constant factor. So that's one coding trick. Now it turns out that you can actually go further, and there's a fairly sophisticated algorithm that's sort of beyond the scope of 6006. That's an in-place merge sort. And this in-place merge sort is kind of impractical in the sense that it doesn't do very well in terms of the constant factor. So while it's in place and it's still theta n log n, the problem is that the running time of an in-place merge sort is much worse than the regular merge sort that uses theta n auxiliary space. So people don't really use in-place merge sort. It's a great paper. It's a great thing to read. Its analysis is a bit sophisticated for 006, so we won't go there. But it does exist. So you can take merge sort. I just want to let you know that you can do things in place. In terms of numbers, some experiments we ran a few years ago, so these may not be completely valid because I'm going to actually give you numbers. But merge sort in Python, if you write a little curve fit program to do this, is 2.2 n log n microseconds. Okay, for a given n. Right. So this is the merge sort routine. And if you look at insertion sort in Python, that's something like 0.2 n square microseconds. Okay, so you see the constant factors here. If you do insertion sort in C, which is a compiled language, then it's much faster. It's about 20 times faster. It's 0.01 n square microseconds. Okay, so a little bit of practice on the side. We do ask you to write code, and this is important. The reason we're interested in algorithms is because people want to run them. And what you can see is that you can actually find an n. So regardless of whether you're Python or C, this sort of tells you that asymptotic complexity is pretty important, because once n gets beyond about 4,000, you're going to see that merge sort in Python beats insertion sort in C. Right? So the constant factors get subsumed beyond certain values of n. So that's why asymptotic complexity is important. You do have a factor of 20 here, but that doesn't really help you in terms of keeping an n square algorithm competitive. It stays competitive for a little bit longer, but then falls behind. All right? Okay, so that's what I want to cover for sorting. So hopefully you have a sense of what happens with these two sorting algorithms. We'll look at a very different sorting algorithm next time using heaps, which is a different data structure. The last thing I want to do in the couple of minutes I have left is give you a little more intuition as to recurrence solving based on this diagram that I wrote up there. And so we're going to use exactly this structure, and we're going to look at a couple of different recurrences that I won't really motivate in terms of having a specific algorithm, but I'll just write out the recurrence, and we look at the recursion tree for that, and I'll try and tease out of you the complexity associated with these recurrences, or the overall complexity. So let's take a look at t of n equals 2t of n over 2 plus cn squared. Okay, c times n, or let me just call that cn. No need for the brackets. So constant c times n squared. So if you had a crummy merge routine and it was taking n squared and you coded it up wrong, that would be it's not a great motivation for this recurrence, but it is a way this recurrence could have come up. All right. So what does this recursive tree look like? Well, it looks kind of the same. Obviously, you have cn squared. You have cn squared divided by 4, cn squared divided by 4, cn squared divided by 16, 4 times. Looking a little bit different from the other one. The levels and the leaves are exactly the same. Eventually, n is going to go down to 1. So you will see c all the way here, and you're going to have n leaves. And you will have, as before, 1 plus log n levels. Everything is the same. Right? And this is why I like this recursive tree formulation so much, because now all I have to do is add up the work associated with each of the levels to get the solution to the recurrence. Right? Now take a look at what happens here. cn squared divided by 2. cn squared divided by 4. And this is n times c. Right? So what does that add up to? Yeah. Yeah, exactly. Exactly right. So if you look at what happens here, this dominates. All of the other things are actually less than that. Okay? And you said bounded by 2cn squared because this part is bounded by cn squared and you already have cn squared up at the top. Right? So this particular algorithm that corresponds to this crummy merge sort, or wherever this recurrence came from, is a theta n square algorithm. And in this case, all of the work done is at the root, at the top level of the recursion. Okay? Here, there was a roughly equal amount of work done in each of the different levels. All right? Here, all of the work was done at the root. Okay? And so to close up shop here, let me just give you real quick a recurrence where all of the work is done at the root, just for closure. So if I had magically a merge routine that actually happened in constant time, either through buggy analysis or because it's buggy, then what does the tree look like for that? And I can think of this as being theta 1, or I can think of this as being just a constant c. I'll stick with that. So I have c, 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 and whoa, I tried to move that up. That doesn't work. So I have n leaves as before. And so if I look at what I have here, I have c at the top level, I have 2c, and so on and so forth, 4c, and then I go all the way down to nc. All right? And so what happens here is this dominates. And so in this recurrence, the whole thing runs in theta n. So what the solution to that is theta n. And what you have here is all of the work being done at the leads. All right? You're not going to really cover this theorem that gives you a mechanical way of figuring this out, because we think the recursive tree is a better way of looking at it. But you can see that depending on what that function is, in terms of the work being done in the merge routine, you have different versions of recurrences. All right? I'll stick around, and people who answer questions, please pick up your questions. See you next time.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
One of the cutest little data structures that was ever invented, called a heap. And we're going to use the heap as an example implementation of a priority queue. And we'll also use heaps to build a sorting algorithm called heap sort that is very, very different from either insertion sort or merge sort. And it has some nice properties that neither insertion sort nor merge sort have. But what I want to do is get started with motivating the heap data structure, regardless of whether you're interested in sorting or not. So the notion of priority queue, I think, makes intuitive sense to all of you. It's essentially a structure that implements a set S of elements. And each of these elements is associated with a key. And as you can imagine, a priority queue is something where you queue up for something, you want to buy something, you want to sell something, you have certain priorities assigned to you, and you want to pick the maximum priority or the min priority, you want to be able to delete it from the queue, you want to be able to insert things into this queue, you want to be able to change priorities in the queue. So all of these operations are interesting operations that should run fast, and for some definition of fast. Obviously, we're interested in the asymptotic complexity definition of fast. In that case, we'll be saying, does this operation run in order n time, order log n time, etc. So in general, I think for the next few lectures, you're going to see a specification of a data structure in terms of the operations that the data structure should perform. And those of you who have taken 6.05, you'll see that it's basically an abstract data type that's associated with these operations, so it's a spec for the abstract data type. In 6.05, you didn't really spend a lot of time on asymptotic complexity or the efficiency of operations on the abstract data type. Here in 006, you'll specify this ADT and specify the set of operations or methods in the ADT, and we'll talk about whether these are order n complexity or order n log n complexity, and compare and contrast different ADTs. So today's ADT is a heap. And so what is the set of operations that we like to perform on a priority queue? So we can use that to motivate the development of a heap, and those are insert SX. So you have a set of elements S, and you want to be able to insert element X into set S. You want to be able to do max of S, which is return the element of S with the largest key. And different from max of X, S rather, is extract max of S, which not only returns the element with the largest key, but also removes it from S. So this is, you have a queue, and the person in the queue was serviced, or the element in the queue was serviced, and then removed from the queue. And finally, you can imagine changing the priority of a particular element X in the set S, and this priority, there's an associated key, as we have up there with each element, and that key is, call it K, and increased key S, X, K would increase the value of X's key to the new value K. Right. And K could correspond to, it's just called increase. Most of the time, you're increasing the value in maybe a particular application. You can have certainly a decrease key, and you'd have to know what the previous value was. And it's just a matter of exactly what operation you want to perform. You could call it update or increment, whatever you like. I'm going to spend most of the time here talking about how you maintain a rep invariant of this data structure called the heap that allows you to do these operations in an efficient way. And we'll talk about what the efficiency is, and we'll try and analyze the efficiency of these algorithms that we put up. All right? So let's talk about a heap. A heap is an implementation of a priority queue. It's amazingly an array structure, except that you're visualizing this array as a nearly complete binary tree. And so what does that mean exactly? Well, the best way to understand that is by looking at an example. Just 10 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here's my array of 10 elements, and the elements are 16, 14, 10, 8, 7. So some set of elements, they're in random order, clearly not sorted. And I'm looking at the indices and I'm looking at the elements, and I'm going to visualize this as a nearly complete binary tree. It's not a full binary tree because I only have 10 elements in it, and it would have to have 15 elements to be a complete binary tree. And you want to be able to do the general case of an arbitrary size array, and so that's why we have a nearly complete here. So what does it mean to visualize this as a tree? Well, index 1 is the root of the tree, and that's an item with the value 16. And what I have are indices 2 and 3 are the children, and 4, 5, 6, and 7 are the children of 2 and 3, and 8, 9, and 10 are the children of 4 and 5 in this case. And so that's the picture you want to keep in your head for the rest of this lecture. Anytime you see an array, you say we're going to be looking at the heap representation of the array. The picture on the right tells you what the heap looks like. And so I'm not going to fill in all of these, but I'll do a couple. So you have 10 here, and 8, 7, etc. So that's a heap structure. So what's nice about this heap structure is that you'll have a tree representation of an array, and that lets you do a bunch of interesting things. What do you get out of this visualization? Well, the root of the tree is the first element, corresponding to I equals 1. The parent of I is I over 2. The left child of I is 2i, and the right child of I is 2i plus 1. Right. So that's essentially what this mapping corresponds to. Now on top of that, this is just what a heap corresponds to. We're going to have particular types of heaps that we call max heaps and min heaps. And as you can imagine, max heaps and min heaps have additional properties on top of the basic heap structure. So this is essentially a definition of a heap. Now I'm going to define what the max heap property is. And the max heap property says that the key of a node is greater than or equal to the keys of its children. Okay, that's it. It's obviously recursive in the sense that you have to have this true for every node in the tree. And when you get down to the leaves of the tree, they're not children corresponding to the leaves, so that's a trivial property. But at higher levels, you're going to have children, and you have to check that. So if you look at this example here, maybe I should fill this whole thing out. So I have 8 and 7 here, and 6 would be 9, and I have 3 over here, and then 2, 4, 1. Right? So we can look at this and check whether it has the max heap property or not. Does it have the max heap property? This heap? Yeah. All you have to do is look at these nodes, 1, 2, 3 indices, index 4, 5, 6, and well, you don't have to look at 6 and 7 because they don't have any children. But you can start with 5 here, and you look at the children, and there you go. The parent is greater than or equal to either of its children or its only child in the case of node 5, and so you have the max heap property. Right, so fairly straightforward property. And you can imagine defining the min heap property in an equivalent way. Right? Just replace the greater than or equal to with less than or equal to. So right off the bat, what operation is going to be trivially performed on a max heap? This is a kind of a trivial question, but yeah. Just finding the biggest element, exactly right. The max operation. Now, what about extract max? Is that trivially performed on a max heap? No, because, so what do I mean by that? When you say a max is trivially performed, what it means is that you can return the max. You can find the maximum element, or the maximum element, and you obviously don't modify the heap, and the heap stays the same, so it stays a max heap. In general, when we talk about data structures, and this goes back to rep invariance, which I've mentioned already, you typically want to maintain this rep invariant, and so the rep invariant of our data structure, in this case, is a max heap property. Okay, so we want to maintain the max heap property as we modify the heap. So we go from one heap to another, you start with the max heap, you want to end with the max heap. Okay, and it makes perfect sense because one of the simplest things that you want to do in a priority queue is you want to be able to create a priority queue, and you want to be able to run extract max on the priority queue over and over, right? And what that means is that you take a max element, you delete it, take the next max element, delete it, and so on and so forth, and there you go. All right? And it's a bit of a preview here, but you can imagine that if you did that, you would get a sorted list of elements in decreasing order, right? So you see the connection to sorting, because you can imagine that once we have this heap structure and we can maintain the max heap property, that we could continually run extract max on it. And if you could build extract max in an efficient way, you might have a fantastic sorting algorithm. All right? So the big question that really remains is how do we maintain the max heap property as we modify the heap? Okay, and how would you go? The other question, which I haven't answered, is there's this array that turns out it was a max heap. Okay, but it's quite possible that I have a trivial example of an array. In fact, let me make this one. That is not a max heap. It's not a max heap. It's not a min heap. It's neither. Right? It's just a heap. Okay. So if I just transform or visualize, I should say, this array as a heap, I don't have a max heap. I don't have a min heap. So if I were interested in sorting, and I am, there's another thing that's sort of missing here that we have to work on, which is how are we going to build a max heap out of an initially unsorted array, right? Which may or may not turn into a max heap. This trivially happened to be exactly the right thing because I picked it and it turned into a max heap just by visualizing it. But it's quite possible that you have arrays that are input to your sorting algorithm that look like that, right? Yep. Okay, so let's dive into heap operations. I'm going to have spent some time describing to you a bunch of different methods that you would call on a heap, and all of these methods are going to have to maintain our representation invariant or the max heap property. So what are the heap operations that we have to implement and analyze the complexity for? Well, we're going to have build max heap, which produces a max heap from an arbitrary or unordered array. So somehow I got to turn this into, for example, 4, 2, 1. Okay? This is in effect sorting this array, right? Or changing the order. Maybe not fully sorting it, but changing the order. So that's what I'll have to do. And build max heap is going to have to do that. In order to do build max heap, the first procedure that I'm going to describe to you is called max heapify, right? Heapify, right? Sounds a little strange, but I guess you can defy pretty much anything. So you correct a single violation of the heap property in a subtree, subtree's root. Okay, and I'll explain what I mean by that in just a minute. So max heapify is the fundamental operation that we have to understand here, and we're going to use it over and over. What it does is take something that is not a heap, not a max heap. When I say not a heap from now on, pretend that I'm saying not a max heap. We're only going to be talking about max heaps for the rest of this lecture. Okay, and what max heapify does is take something that is not quite a max heap. It can't take anything arbitrary. It's going to take something where there's a single violation of the max heap property at some subtree of this heap that is given to you, and there's a single violation of that. And it's going to fix that. Okay, and we need to be able to do this recursively at different levels to build an max heap from an unordered array. And then once we have that, we need to work out the things like insert and extract max and heap sort and so on and so forth. So let's take a look at max heapify as an example. I'm not going to write pseudocode for max heapify. I'll run through an example and the pseudocode is in the notes. The big assumption, the precondition for running max heapify is that the trees rooted at left eye and right eye are max heap. So max heapify is going to look like A comma I. A is simply the array, and I is the index. Okay, and max heapify is willing to, you're allowed to crash and not do anything useful if this precondition is violated in max heapify. But if the precondition is true, then what you have to do is you have to return a max heap correcting this violation. All right, that's the contract. So let's take a look at an example. I think what I want to do is start over here. I want you to see all of the steps here. So we take a simple example and we run through max heapify. And let's take a look at 16 for and I'm just going to draw the indices for this first example, and then I won't bother. So there you go. Is this a max heap? No, because right here I got a problem. 4 is less than 14, therefore I have a violation, right? And so if you look at the call max heapify 8, 2,